Now in this lecture we will discuss about first order reaction. Let us say we have a general reaction reactant A, and this gives product. Rate constant for this reaction is K. So we can write rate of decay of A, that is minus K times concentration of A. We have negative sign because as time increases concentration of A decreases. It decreases as time increases. In other words, we can also say this is minus because this is a decay. So negative because there is a decomposition. So we can write rate log N if I take A this side, we will have dA by A, concentration of A, minus K dt. Let us say we have been given T is equals to 0, concentration of A is A naught, and T is equals to T, concentration of A, this is also given, AT. Then we can find a relationship between time, concentration of AT, rate constant K. So let us integrate both sides. We have 0, time is T, initial concentration is A naught, concentration after time T is AT. So we will have ln A, and integration from A naught to AT. This is minus KT. So we will have ln AT minus ln A naught minus KT. So ln A minus ln B is equals to ln A by B. We can absorb negative sign. Negative sign will go on power. So we can write KT is equals to ln A naught by AT. We can convert log, ln into log, this is based on E, so we can convert on base of 10 if I multiply by 2.303. So from here we can write T is equals to 2.303 by K log A naught by AT. A naught is the initial concentration and AT is the concentration after time T. So this expression we have to remember. Same expression we can also write in a different form. Let us consider this expression. ln AT by A naught is equals to minus KT. So we can write from here AT by A naught is equals to e to the power minus kt. So we can write AT is equals to A naught e to the power minus kt. So one has to remember this expression. Concentration of A at any time t is given by this expression. This expression can also be written in a different form. A goes to product. If initial concentration of A is a small a, product is 0, x mole of A is decomposed, so left mole of A is A minus x and mole of product formed is x. So A minus x, that is left mole of A. That is basically, if the volume is constant, this is also related to concentration, or we can say left mole of or mole of A at time t. So this is mole of A at time t. Similarly, A is the initial mole of So this expression can also be written in a different form. So we have T is equals to 2.303 by K log of concentration of A naught, that is initial concentration, concentration after time T. Let us say V is the volume of vessel or volume of solution. If reaction is happening in solution phase, then this is the volume of solution. If reaction is happening in gas phase, then this is the volume of container. So we can write 2.303 by K. Initial concentration is A by V. Concentration after time T is A minus x by V. So this equation is 2.303 by K log of A by A minus x. So one can remember this expression. T is equals to 2.303 by K log A by A minus x. Now important point, we have A is the initial mole and A minus x is the left mole. For example, let us say if I ask find time for 90% completion of reaction, that is reaction is 90% complete. This means we have 10% left. So we can find time is equals to 2.303 by K. Initial is 100 and left is 10. So this is log 10 and log 10 is 1. So we will have simply 2.303 by K. Now if I say find time for 99% completion, completion of reaction. So this means we have 99% complete and we have 1% incomplete, that is left. So we can use this equation. So T is equals to 2.303 by K, left is 1, log 100 is 2, so we will have 2 into 2.303 by k. We can similarly calculate time required for 99.9% completion. So in this case we have 99.9% complete. So this means 0.1% is only incomplete, that is left. So we can find time is equals to log 100 by 0.1 10 to the power 3, that is 3. So we will have 3 into so basically we can make a table. We have 90% completion, 99% completion, 99.9% completion. We can also rate 99.99 completion. In this case we will have time, that is 2.303 by k. So let us call 2.303 by k is t0. So in first case time required is t0, second case 2 t0, 3 t0, 4 t0. So this is the time required for different cases. You see, difference in each case is t0. In first case reaction is 90% complete. In the second case reaction is only 9% complete. In the next case reaction is only 0.9% complete. And in the next case reaction is only 0.09% extra complete. So you can see clearly reaction is becoming slower and slower. So initial t0 time 90% complete. Next t0 only 9% complete. Next t0 that is only 0.9% complete. Next t0 so 0.09% complete. So you see initially reaction is very fast, but slowly reaction becomes slower. So we can say as time goes reaction becomes slower. That is, it takes more time for completion of a small fraction. So you can see clearly, basically reaction will take infinite time to complete. So we can say theoretically reaction will take infinite time. This is not the case with zero order reaction. If you remember, zero order reaction, it takes finite time to complete, and that time is A by K. So this is the time required for completion. that is, it has a finite time. But in case of first order reaction, this is an infinite time. And this is logical also. If you see first order reaction, dA by dt is minus k times concentration of A. If the concentration decreases, rate decreases. When concentration is very low, rate is very low. So rate is becoming slower and slower. So if concentration is very low, rate is very low, so it will take infinite time. Basically, we can use this expression to make a plot between A versus time. So AT is equals to, so we have expression A naught e to the power minus kt. So we can make a plot. On the y-axis we can plot concentration of T at time t, and on x-axis we will have time. At t is equals to 0, concentration is A naught. So this concentration is A naught. As time increases, concentration decreases and it goes up to infinite. You see, in the first t naught time, so this is first t naught, reaction is 90% complete. In the next t naught time, reaction is only 9% complete. So this is 90% completion. Next t naught, only 9% completion. And in the next t naught, we have only 0.9% completion. And in the next t naught we will have, so here we have t naught, so this value is only 0.09%. So reaction becomes slower and slower. Now next thing we'll discuss about half-life. And this is denoted by T half. It is the time when concentration of reactant becomes half of the initial value. For example, if T is equals to 0, concentration of reactant, this is A naught, then after time T half, this becomes A naught by 2. Now we can calculate T half by 2 ways. If you remember, we have expression dA by A is equals to minus k dt. Now we can integrate from 0, at t equals to 0 concentration is A naught, to T half. At T half concentration is A naught by 2. So we can integrate this expression ln A, and limit is A naught to A naught by 2 minus k T half. So we will have ln A naught by 2, this divided by A naught, is equals to minus k T half. From here we can write ln half is equals to minus k T half, or we can write minus ln 2, so minus goes. So from here we can write T half is equals to ln 2 by k, ln2, this is on the base of e, we can change into the base of 10. So this is 2.303 log 2 divided by k. Log 2 is 0.303. So this is 0.30. Let us take approximate value. So t half becomes 0.693 by k. We can also find this expression directly using equation for first order reaction. So first order reaction we have this is the expression we know. And now in this expression we can directly put the value of AT, that is A naught by 2, then time becomes t half. So this time we will have t half is equals to 2.303 log 2. So this becomes 0.693 by k. So we have t half is equals to 0.693 by k. Important point we have, half-life is independent from initial concentration of reactant. So we does not have any initial concentration in the expression for t half. So we can say t half for first order reaction is independent from initial concentration. So let us say we have initial concentration is A naught. After first t half, it will remain only A naught by 2. If I have next t half, the concentration of A left will be A naught by 2 to the power 2. So this is left concentration. Next t half, we will have A naught divided by 2 to the power 3. So similarly, if I write for nth half-life, that is nth half-life, first half-life 2 to the power 1, second half-life 2 to the power 2, third half-life 2 to the power 3. So you will have nth half-life, left concentration of A will be 2 to the power n. So we can say after nth half-life, left concentration of A naught by 2 to the power n. So we can write A naught in terms of concentration, or we can also write in terms of mole, that is A naught is simply A 2 to the power n. So we can write after nth half-life, decayed concentration of and this will be initial concentration of A is A naught, and this is left. So we have to subtract this value A naught by 2 to the power n. So this is the left concentration. So this will become A naught 2 to the power n minus 1 divided by 2 to the power n. In terms of mole, we can also write and this will be A into 2 to the power n minus 1 divided by 2 to the power n. This result can also be proved by adding all the decayed concentration. You see, after first half-life, decayed is A naught by 2. After second half-life, decayed is A naught by 2 to the power 2. So if I add all these values, we will get the same result. So this result can also be found by adding all the decayed moles. For example, first half-life decayed is A naught by 2, that is, let us say, write in terms of mole. Second half-life 2 to the power 2, 2 to the power 3, finally this is 2 to the power n. So we have to sum this value. So let us take A by 2 common. So we will have 1 plus 1 by 2 now this is a sum of geometric progression, so GP, and this sum is 1 minus r to the power n 1 minus r, where r is the common ratio. In this case we have common ratio is 1 by 2, so each term is multiplied by 1 by 2. So A by 2 1 by 2 to the power n 1 minus 1 by 2. So this becomes simply 1 minus 1 by 2 to the power n so this is the same value we are getting here, that is decayed moles is A into 2 to the power n minus 1 divided by 2 to the power n. We have one important result for first order reaction, that is time taken for any percentage completion in a first order reaction is independent from initial concentration. Initial concentration of reactant. This can be easily verified. Let us take a special case, alpha percent. Initial moles of A is A and alpha percent decayed. So this means decayed is A into alpha by 100. So this is decayed. So what is the left mole of A? This will be A minus A into alpha by 100, that is A into 1 minus alpha by 100. Now we can write this expression, time is equals to 2.303 by K so initial mole is A, left mole is A into alpha by 100. So A cancels. So you see, from here we can clearly see the time required for alpha percent completion does not depend upon initial concentration. So this expression does not have initial concentration. So does not depend upon initial concentration.